Welcome to Data Science with EJD. In this video, I'll be talking about transfer learning. That still comes under advanced supervised learning, right? We've at some point we already saw that. Of course, the broad data playlist is about data science. So drilling down, we discovered that machine learning is part of data science, and trying to see what machine learning is about, we discovered that can be machine learning. Machine learning is the process by which models learn from data, basically. And then from there we saw that machine learning can be subdivided into supervised learning, unsupervised learning, and reinforcement learning. So we took supervised learning, and that's what we're still dealing with. So for supervised learning, we saw that basically two types of supervised learning. Those are classification and regression algorithms. So we've taken the different algorithms under this, though not exhaustive, but at least the key ones, we've taken them. So now I've been talking about advanced supervised learning. So some extra things we can do apart from the basic classification and regression tasks that can be done. So here we're talking about transfer learning. So, transfer learning is actually a powerful deep learning technique. So it's like we're already beginning to step into the realm of deep learning by looking at transfer learning, right? So, transfer learning is a powerful deep learning technique that leverages the knowledge gained by a pre-trained model on a large data set, e.g., ImageNet, and applies it to a new but related task, right? So, you have a pre-trained model, and then you're now using it to a task that is related to what it was pre-trained on. Although transfer learning is most commonly used in image-related tasks, so it's very good for when you are working with images. It can also be creatively adapted to non-image data, such as the iris dataset, that's the iris flower that we've been talking about all along. So it's a classic tabular dataset consisting of 150 samples with four numerical features, each classified into three species of iris flowers. While this is not a typical application, of course, you should know deep learning deals with more serious stuff than just the simple iris dataset. But this is just for educational purposes alone, right? So while this is not a typical application, it provides an excellent educational example of how data modality transformations can make unconventional use of image-based neural networks like ResNet. Okay, let's look at the learning objective. It's understand the core concept of transfer learning, then apply a pre-trained ResNet model to a non-image dataset, that's the iris dataset, by transforming the data into a compatible image-like format. So there's a kind of transformation we'll have to do on that iris dataset to make it look like we're working with image. So we can also fine-tune the model's final layer to perform classification on a three-class problem. Okay, so conceptual foundation of transfer learning. Transfer learning involves taking a model pre-trained on a large data set and adapting it to a smaller, often task-specific data set. In CNN, I believe that's convolutional neural networks like ResNet. Early layers capture general visual patterns like edges, textures, while later layers capture task-specific features. Now, while we're using the iris dataset, though it's not like the most suitable thing we can do. So the iris dataset is not image-based, but for demonstration, we can reshape each sample into an image-like tensor to impute into ResNet. So this requires creative preprocessing to reshape the 4D numerical data into a 3224 tensor expected by ResNet. So it's like we're doing a bit of modification to the iris dataset to be able to use it in this case. So of course, for the umpteenth time, the dataset summary, we have four features: sepal length, sepal width, petal length, petal width for the iris dataset, and we have three classes. That's talking about species now. Setosa species, vesicular species, and Virginica species. And there are 150 samples, so we have 150 samples, and they are divided into three species, 50 of Setosa, 50 of vesicular, 50 of Virginica. And then the methodology, we normalize features using standard scaling. So when we are doing something like this, right, normalization is really important so that we can get a more accurate result. Then we can transform each four-dimensional feature vector into a synthetic image-like tensor, e.g., tile or interpolate to a 3 by 2 to 4 by 2 to 4 format. Then we prepare the ResNet model. So where we load a pre-trained ResNet 18, then we place the final fully connected layer to output three classes, and then we freeze all pre-trained layers except the final classification layer. Now things are getting really complicated, right? As you can imagine. So step three, train and evaluate. So you use cross entropy loss and Adam optimizer. I mean, we used Adam optimizer in the last video where we talked about some using neural network for some kind of supervised tasks. Then you train only the final layer to avoid overfitting due to limited data. Then you evaluate accuracy on a held out test set. Now, the held out test set, that's what we've been doing all along. When you take 80% of the data set for training and you hold out 20%, you just keep it somewhere. So by the time you're done training the model, then you can now test it on that held out test set. Now let's look at the code implementation using Torch. That's PyTorch. Here's the complete systematic implementation. First of all, the Torch is a new library that we are dealing with here. So you have to install Torch. So you install that. That takes a bit of time. I'd installed it before, so it will not take so long anymore. Then apart from that, we also need Touch Vision. You have to install that separately. So people install Touch Vision. So that's also done. And then we can now go and look at the data and look at the code now. So import touch.nn as nn, that's neural network now. Import touch.optim as optim, that's like you're trying to optimize something, I believe. So from touch vision models, so import ResNet 18 weights. Then of course we are loading the iris data set. That's what we're using for this. Then for model selection, we need train test set. Then we need the standard scalar. For metrics, we need confusion matrix display. Then we need matplotlib for for plots, and we need numpy for numerical calculations. So here, so we load and pre-process the iris data sets. Let me try to put uh line numbers for easy referencing. Okay, so here now we load the data set that's from 13 to 15. Then we do the scaling thing here. That's us trying to transform the data in a way that is useful. Then okay, I think this is where we have some kind of preprocessing. I think I rather call that like step two. So data. Okay, I mean everything is preprocessing, right? It's been labeled up there. So that's preprocessing. That's normalizing the data set. Then we have a function, a Python function called vector to image. So we want to turn our vector to image since we are dealing with data, iris data set, which is not an image data set. So this is us trying to transform that. So you have img np.tile. So you want to convert vector to image now. So 112 by 112, comma 3 and all this. So this whole thing is for that. Then for the X images, now you now have np.array vector to image, the sample for sample in X scaled, then Y tensor, you have touch.tensor, blah blah. And then this is where you're training the data set, right? So so here now you have X train X test, Y train Y test as usual. Then you're using 30% in this case. You're holding out 30% while you're training the model with 70%. All right. So you also have so for the train data set, so you have something you have touch.utils data tensor data set, touch.tensor, X train d type touch, blah blah blah. So you have this whole thing now, bringing the whole tensor thing here. And then next you have to load pre-trained ResNet and modify. So the whole idea of transfer learning is you have a model you have trained on a large data set. You're now using it for something similar. So we have the weights now, ResNet underscore weight dot net image net ik underscore vi. ResNet is its own weight equals weight. So for parameter and ResNet the parameters, you now have parameter dot requires undergrad underscore grad equals false, and then you have this whole ResNet thing going on here. For parameter ResNet, you have all of this at the end of the day. So for device, you have touch device CUDA. If touch CUDA is available, else CPU, then ResNet to device. Criterion, neural network cross entropy loss. Optimizer, that's the Adam optimizer. Then you can now do the train with loss tracking. So this takes a long process, right? So when it comes begins to talk about neural networks, you see that things begin to take a lot of time because it's more like walking through several networks at the same time. So then you now go on for the to plot the training loss to see what things look like over the epochs, and then you can evaluate with confusion matrix, right? And then So, these are all the process you need to do for that. Don't forget you have access to this whole code sheet by just looking at the description box, or whether on Facebook or on YouTube. Just click and you can download all these things. In fact, you should download first before you start following the class, so that you can do it hands-on and see what happens. So all of these things I'm just going to run in one blow. All right. So we have this now, and uh, so I think it's still. Yeah, it's still running, so it's a lot, right? So when it starts, you begin to see, uh, yeah, so the training is on, right? Because it takes quite a while. Then Epoch 1, the loss is 7.9028. Okay, Epoch 2, the loss is 6.04, so it's getting better. Epoch 3, the loss is 5.0091. Epoch 4, it's now 4.6998. Epoch 5, it's 4.3658. So we have it in five epochs. So you see, we said the epoch should be five, right? If you want more epochs, you can actually increase it there. So, and the more the epochs go, the better the results get, right? So, depending on what you want, right, you can actually determine. So, in five epochs, right, the test accuracy gives us 86.67%, right? In this case. And then you have the confusion matrix like this. So, these are I think these are all the true positives or something like that. Then these other ones are the false negatives and false positives and the rest of them. Okay. So, you have all of that going on there. Then so that's how that is as far as transfer learning is concerned. A model that has been trained on a large data set, you now use it for a smaller data set. So notes and caveats that we should pay attention to. This method is purely educational, just like we said. We use the iris dataset, which is not actually an image thing. So these things are basically used on image stuff, right? So this method is purely educational. Real world usage of transfer learning with tabular data would benefit from pre-trained models for structured data like TabNet, Saint, or FT Transformer. Artificially expanding 4D tabular vectors into high-dimensional images does not improve predictive power, but it slows how ResNet can be structurally adapted to new tasks. So data augmentation is not needed here due to synthetic input. So you can see this is purely for educational purposes. So it just gives you an idea into what transfer learning is about. So looking at the components and their descriptions now. For the data set, we have iris, four features, 150 samples, three classes. The input transformation, we have to do feature vector to pseudo image of 3 by 24 by 24 by 224 by 224. Then the model is ResNet 18 pretend on ImageNet. Then we're now using it on this iris dataset. Then the output layer is such that we have replaced FC layer to three output neurons. I think we saw FC before. I've forgotten what FC is. I think it's something. Let's see. Yeah, fully connected. Yeah, fully connected. So we have to replace fully connected layer, and then we have three output neurons. Then the strategy is to freeze pre-trained layers, train only final layer, and the result effective fine-tuning and demonstration of transfer learning. So that's all. That's like our introduction to transfer learning. So it's possible to use a pre-trained model on a large data set on similar data set that are not so large, right? So with this, we come to the end of this video. Let me know if there's something you like on the tryout. Let me know how helpful this video is for you. Also, if you have subscribed, thank you for that. If you haven't subscribed, feel free to do that right now and hit the notification bell so you can always get alerted each time a new video is released. On my channel, you can now become a member. You can have bronze access, silver access, or gold access, and this grants you different layers of privileges, like having a badge displayed close to your name, on my channel, and then you can actually get my PDF notes, the PDF notes from my mathematics lectures on request. You can also get some videos exclusively for only members. Then you can get some you can also have one-on-one consultations with me depending on the level of membership you belong to. All right. So be sure to like and share this video so that more people can have access to the information I have going on here. Till I come your way again, keep doing data right. Bye.